Hi, my name is Marcelo de Castro Fernandes. I am a Ph.D. student at Rensselaer Polytechnic Institute, working under the guidance of Dr. Luigi Vanfredi, and I will present a summary of my research on heterogeneous modeling and simulation for control design of battery energy storage systems. In the field of power systems, we have basically divided the studies depending on the time constants involved in the phenomena being observed. Transient stability phenomena in transmission and distribution systems is usually studied using phasor-based models, while power electronic devices are usually simulated using electromagnetic equations and discretization of differential equations. And because of that, the tools are usually specialized in one paradigm, and analysis is conducted in different and independent tools. Hence, the analysis and control design of different systems is conducted separately, not allowing us to observe interesting and important phenomena such as resonances, distortions, maybe even control interactions. And for example, phasor-based models will require oversimplification of power electronic devices, while EMT models are too detailed for the representation of large systems. And in order to overcome this issue, we proposed a hybrid interface. But I'm not talking about just a co-simulation hybrid interface. I'm talking about using Modelica to create a heterogeneous model that unify both EMT and phasor-based models at the equation level using a filter and a phase-locked loop. And in order to demonstrate this idea, we assembled a small single machine system representing the bulk power system and model it, which is modeled in a phasor domain and is highlighted here, represented here in the blue square. We also modeled the battery energy storage system in detail with all the converters and necessary details. And here it is represented in orange. And as you can see, all the converters are represented in the green square, and the frequency and voltage controls, you can check them in the red squares. So you have all the details there. And using this approach, we could linearize the entire system, okay, because it was basically built under the same equation-based platform. And we could check the eigenvalues that represented poorly damped oscillations, and we could perform root locus analysis to properly tune the battery controllers, as you can see in the center figure and the right-hand figure. We could set the parameters of the battery's controller there by making root locus analysis in the entire system. And as you can see, in the left part of this slide, you can see the results. And as you can see, we were able to damp oscillations that were poorly damped before without the battery system. And in your right, you can see that the hybrid interface allows us to check variables from inside the battery, for example, the capacitor voltage in the DC bus. And we can also see the variables, how they change representation in the interface, in the hybrid interface. For example, you can see the currents being represented as waves in the center figure in your right part. And you can see the same currents being represented as real and imaginary parts of the phasor representation right below it. Therefore, in this work, we were able to create a battery model in Modelica that can have different levels of details. And in addition, the hybrid interface was assembled also using Modelica. And it unified different systems at the equation level. This fact allowed us to perform modeling, simulation, linear analysis, and control design using the same model and the same tool. Thank you very much.